In recent years, using pulsar timing arrays, scientists have detected the lowest frequency gravitational waves ever observed so far. Nanohertz gravitational waves. These gravitational waves are generally believed to originate from the depths of the universe, where many supermassive black holes with masses billions of times that of the Sun are hidden. When these giants collide and merge with each other, the surrounding spacetime is slowly disturbed by enormous changes in gravity, thereby producing extremely low-frequency gravitational waves. These gravitational wave signals permeate the universe like a background noise. This indicates that, throughout the universe, especially in its early stages, the mergers of supermassive black holes, or equivalently the mergers of galaxies, were very common. However, black hole mergers are far from as simple as they might seem, if quantum effects are taken into account. As two black holes continue to approach each other, the smaller one may be completely evaporated before it has time to merge. In other words, when general relativity and quantum field theory are both considered simultaneously, black hole mergers would not occur at all, even if quantum effects are ignored. The merger of supermassive black holes at galactic centers still presents unresolved puzzles. It is generally believed that a black hole merger proceeds in three stages: inspiral, merger, and ring down. During the inspiral phase, the two black holes orbit each other while gradually drawing closer. This process emits extremely low-frequency gravitational waves. When the black holes enter the final stage of inspiral, the gravitational waves become very strong, and can be detected by instruments such as LIGO. After that, the merger occurs, and the two black holes ultimately stick together, forming a single new black hole. When the new black hole is first formed, its shape is irregular, and it undergoes a brief oscillatory phase. Soon, however, it settles down, and becomes a stable black hole with a regular shape. This process resembles a ringing bell gradually coming to rest, and is therefore called the ring-down phase. That is the theory, but in reality, for two black holes to gradually approach each other, there must be a mechanism to dissipate their energy. Otherwise, they would enter an extremely long-lasting orbital phase. In the early stages of inspiral, this is not a major problem, as there are many channels through which energy can be dissipated. For example, when supermassive black holes at galactic centers merge, they are surrounded by large numbers of stars and interstellar matter. These stars and gas exert dynamical friction on the black holes. This friction helps the black holes lose angular momentum, thereby shrinking their orbital separation. At the same time, as the black holes orbit each other, the gravitational waves they emit also carry away energy, further tightening the orbit. However, in the final stages of inspiral, when the two black holes are extremely close, there is essentially nothing left around them. They can no longer lose energy through dynamical friction. When the separation between the two black holes shrinks to about 1 parsec, roughly 3.26 light-years, the inspiral process may stall. That is, the two black holes can remain locked at a separation of about 1 parsec for a very long time, unable to complete the merger. This is known as the final parsec problem. The existence of this problem not only conflicts with the theoretical expectations of the gravitational wave background discussed earlier, but also contradicts the idea that supermassive black holes grow through the merger of smaller black holes. Given that black hole mergers clearly do occur in reality, there must be some mechanisms at work that we do not yet fully understand. If we could find two supermassive black holes currently merging at separations smaller than 1 parsec, it might help us resolve the long-standing final parsec problem. However, sub-parsec supermassive binary black holes are usually very distant from Earth. In addition, the two black holes in a binary system often have very different masses, and their accretion behaviors can also differ significantly, making them difficult to distinguish observationally. In November 2023, a paper published in the Astrophysical Journal, by an international research team led by the Shanghai Astronomical Observatory of the Chinese Academy of Sciences, analyzed more than 40 years of observational data from 1978 to 2022. They found that the black hole in the galaxy M81 may actually be a binary system. The two black holes are extremely close, with a separation of only about 0.02 parsecs, making it a textbook example of a subparsec supermassive binary black hole. Such a small separation suggests that the system is already very close to the stage dominated by gravitational wave emission. This, to some extent, indicates that the merger of supermassive black holes does not suffer from a prolonged stalling phase. It provides an important observational reference for addressing the final parsec problem. In July 2024, another paper published in Physical Review Letters proposed a new method to solve the final parsec problem through the self-interaction of dark matter. According to current dark matter theories, in addition to ordinary matter being densely packed at galactic centers, dark matter is also relatively dense there. However, in previous black hole merger models, Rapidly moving black holes generate strong gravitational perturbations, causing dark matter particles to be ejected from the system. When the separation between two black holes approaches 1 parsec, there are not only no stars or interstellar matter left around them, but even dark matter becomes scarce. As a result, their orbits stop shrinking, and the system encounters the final parsec problem. Previously, most studies focused on the interaction between dark matter and black holes. In this new paper, however, researchers assumed that certain dark matter particles can interact with each other. This self-interaction prevents dark matter from being completely dispersed, allowing it to maintain a relatively high density. As a result, the dark matter can continue to interact with the black holes, further draining energy from the system. In this way, the black hole orbits continue to shrink, until the merger is finally completed. The true nature of black hole mergers remains elusive. But what about neutron-star mergers? Do we understand them better? Compared to supermassive black holes, neutron stars present fewer issues in this regard. Although they are also extremely dense objects, their masses are far smaller. For such lower mass objects, the gravitational interaction between them is relatively weaker, and more easily influenced by their surroundings. Moreover, unlike black holes, neutron stars are not purely absorptive. They have many channels through which energy can be dissipated. For example, intense radiation is produced during mergers, and their extremely strong magnetic fields also play an important role. In short, neutron star mergers can be considered free from the so-called final parsec problem. However, even though the inspiral phase is well understood, what happens when the merger actually begins, when the collision occurs, remains an open scientific question. Why is that? Because the conditions during neutron star collisions are extraordinarily extreme. Not only is the state of matter inside neutron stars itself extreme, but the high temperatures and pressures generated during the process are also impossible to reproduce in laboratory experiments. In addition, the physical processes involved in the collision are highly complex, including strong magnetic fields, large angular momentum, and the mixing of various states of matter. On top of that, neutron star collisions are inherently rare, and observational data remain limited. As a result, current theoretical models of neutron star mergers are still highly incomplete, and are largely based on mathematical formulations of general relativity that carry significant uncertainties. In May 2024, a paper published in Physical Review Letters analyzed neutrinos emitted from neutron star merger remnants to gain a glimpse of what happens during these collisions. Before the collision, neutron stars are considered cold, although cold in this context still means temperatures of billions of degrees. At the moment the collision occurs, however, the surface of the neutron stars is rapidly heated to tens of trillions of degrees. Because neutron stars are incredibly dense, photons cannot escape to carry away this heat. During the collision, however, a large number of neutron-neutron interactions produce protons, electrons, and neutrinos. Neutrinos are famously known as ghost particles. They do not participate in strong or electromagnetic interactions. As a result, the neutron star can cool by emitting neutrinos. At the very moment the collision begins, the neutron star's surface becomes unimaginably hot, while its interior remains relatively cool, at temperatures of only a few billion degrees. This imbalance lasts for just 2 to 3 milliseconds, after which the entire neutron star reaches thermal equilibrium. This brief non-equilibrium phase remains a mystery to modern physics. Studying these extreme objects will help us further refine and advance our understanding of fundamental physics.